stay. That's not great. There we go. Cool. So last time, can somebody tell me anything about subtraction, for example? What's a method for subtraction? What's like a type of problem? Say again? Oh, good. Okay.
And then we have.
So a way to do subtraction, you can do missing addend. I love it. Somebody give me an example of missing addend.
3 plus blank equals 7.
Yeah, so make it a subtraction problem.
3
So 7 minus 3 equals what?
would be.
It's the same thing as 7 equals
3 plus what?
3 plus what? Exactly. And again, why is this a good strategy to use this in the early going of subtraction discussion with students?
Another addition.
Yeah, so you want to tie something new in with something they know and they work with, so they feel more comfortable as they reach out for this new stuff, right? So that's missing addend. And we see something very similar with multiplication. What's the similar thing with multiplication?
The community.
So if I say, division, related to multiplication. So if I say 12 divided by 3 is what a student could think.
What times?
Well, no. In terms, sort of something related to missing addend. I can relate the subtraction back to addition by thinking what's missing. 3 plus what is 7. We know that's a subtraction problem, but from a student's perspective, that's just remembering my addition stuff, right? 3 plus what is 7, 3 plus 4, okay. We know they're doing subtraction, they don't even know it. They just think they're doing stuff they've already done. Does that make sense? Then you tell them, hey, you did something new, and you're like, oh, you tricked me. 12 divided by 3 is what? I can think of that as 12 equals 3 times what? So that's the missing factor approach, right? What factor is missing to go with 3 to make it 12? So they will have already known, they know their multiplication table, so it's really just thinking backwards from the multiplication table. Is everybody with me? Yes?
And also for the division, you can do a repeated subtraction.
Yeah, okay, good. So I wanted to start with the first thing somebody told me. Missing addend for subtraction is related to missing factor for division. Now you said, what's another thing for subtraction?
Another thing for subtraction is there's the 2 set models you can draw, which are.
So we got set method for solving a subtraction problem, right? And of course, set method actually is kind of like sits above these things. You can use set method, you can use missing addend approach. How would you do that? So if I had to do 5 minus 3 and I want to do a missing addend approach, I'd put 3 and I can compare that with 5 and say what's missing here to make it the same, right?
Yeah.
All right, let me think. I'm thinking silly. Well, actually, that's fine.
That makes sense.
That makes sense. Okay. So I can think, what would I have to add to this to make it 5? And whatever I do, that would be what 5 minus 3 is. Okay, so I don't want to do a comparison. This is a different thing. So set method can be used for subtraction, multiplication. It can be used for division, addition. It can be used to represent missing addend. What's another thing for subtraction besides missing addend? The main thing people think of when they think subtraction. Takeaway. Now let me put under here, and by the way, don't worry about copying this down. This is just a quick, and you'll see why you don't have to worry about multiplying, writing this down. We'll see. You got measurement here also, so I'll put these together now, right? Measurement is the number line thing, right? You guys all with me? So if I want to do missing addend for with measurement model for 5 minus 3, I'd say if I go 3, how much further do I have to go to get to 5? And that's 5 minus 3. That's kind of like counting on. 5 minus 3 is 3, 4, 5. 5 minus 3 is 2. Because that's how much more I need. Is everybody with me? And again, I know we all know this, but you have to know what the name is. You have to know what it is when you see it in your students. Right? Because some of this stuff we do intuitively. Once we kind of learn a little bit, we start doing some stuff intuitively because we are hardwired to a certain degree to be able to do some of the stuff. Takeaway is exactly what it sounds like. Could you give me a takeaway set method example? Like for 5 minus 3.
You could draw a circle with 5 dots, and then circle 3 of those dots and point an arrow out.
Yeah, so then you'd be left with 2. I love it. Okay, good. I love it. Okay. Kick ass.
I just don't think it's a good idea to use the dotted line, because like a child could get mixed up.
Oh, I see
on
what
the
you mean.
dots.
Yeah, you might. And the beautiful thing about this, you could use colored pencils, and you could say the colors represent certain things. This is where you have certain topics you're going to need to teach. You can choose how to teach them. So, for example, if you use red colored pencil to mean those are what I'm taking out, that's not some standard thing. You know, like America uses red for taking away. No, so every teacher has a certain set number of concepts they have to get across. So at community college level, there's something called a course outline of record. And the course outline of record lists it lists the objectives of the class, it lists the course content, which is basically what we're going to be working with to learn the objectives, blah, 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 right? And this is how we communicate to other colleges what the hell a course is. They look at that and they go, all right, you got everything, looks good, we'll accept it. And that's how we articulate courses with other places. So as a teacher, you get that, and you're like, okay, this is the course. This is very bland. What can I do to accomplish this in a more interesting way? And then that's totally up to you. That's the academic freedom of a teacher, right? Anyway, that's came out of nowhere. Sorry. Okay, and then with division, we've got the missing factor. But what's the most fundamental thing about division? Repeated subtraction. I love it, because multiplication is repeated addition. I love it. Okay. You guys all semi with me? Yes?
So it's safe to say that subtraction and addition is always going to be a missing addend, but division and division is going to be a missing factor.
Yeah, one way to look at subtraction is as a missing addend. So when you tell me what's 10 minus 6, I can think to myself, 6 plus what is 10? Missing addend. Same thing with, does that mean that it's that? No, that's one way to look at it. And one way you can teach it. And again, that's a beautiful bridge from what they just did to what they're doing now. So let me give you this, just because I see a lot of you guys scribbling down this horrendous thing up here. This is just me talking to you, right? What I've done here, let me just give it to you. And I'll tell you. Well,
Sweet, he wrote this for us.
Once.
It's happening.
So this will be really good timing if you missed any recent classes, because don't get used to this, by the way. This is just me saying, hey, the last time I took a class, well, no, that's not true. I took some classes here, because they doubled how much you have to pay now to take a class, so now it's $2 after they take a class. And, you know, fringe benefits because I work here and shit. Come on. But it used to be $1 I could pay to take your class. So I've taken classes here when I actually had time. But I took a paralegal course to get a feel for, because I was thinking about becoming a lawyer, right? And when I took that course, I would write all these notes, and then I would rewrite my notes. Because sometimes something you said later would relate to something you said earlier, and I could put those ideas together. I have no idea what any of you do. So that's why I call this my, what do I call this thing? Notes rewrite example, right? So yes, I have done this for you. This is what you can do to be nice to yourself. Because there's a lot, I don't know if you've noticed, but there's a lot we talk about in this class, yes? So if anybody says to you, oh, you're doing 3 plus 5, you're like, yeah, we're doing the shit out of 3 plus 5. Shut the hell up, right? So like, I remember I took yoga. One of the classes I took here was yoga, and a lot of my friends gave me shit about it. I'm like, you come take one class of this, and let's see how you feel at the end of that damn thing. One thing I loved about yoga is I would play tennis afterwards, and I had yoga legs, meaning I could run forever. Anyway, all of a sudden. So if you look through this really is you don't have to do it like this. I have no idea what you guys do for yourselves. I worry sometimes because in some of my classes, people don't even have paper out. And I'm like, what are you doing right now? What are you doing? You need to write something down, right? And that is really, for me, the way I learn. So one thing that we don't talk in here about, which is unfortunate, which I might try to shoe in sometime, is learning styles versus teaching styles. So when you teach, you try to incorporate a lot of different methods of teaching. And what do I mean by that? Like group work, manipulatives, straight up lecture, videos, whatever. So I try to do that. Sometimes I don't succeed. So, oh well. Does anybody ever heard of the different learning styles? Like there's tactile or kinematic, right?
Oral,
Kinesthetic, oral,
oral, visual.
Yeah, visual.
Audio.
So for me, if I rewrote my notes, the act of rewriting my notes got in my head, and I would never have to look at them again. But the act of rewriting it is what got it. So reorganizing and rewriting it is what got in my head. That might not be true for you. I don't know. So you got to kind of know yourself. There are tests you could take to figure out which one you have, and I might try to find a good one because the one I used before is no longer there, which probably tells me something. But I'll try to find one if you're curious. But when you're teaching, be aware. Bless you. Your students are going to have multiple ways of accepting that. So if you only give one way, you're only helping certain students out, and you're screwing the other students over. Yeah. Blah blah blah. Anyway, so the only reason I give you this, I'm not going to give you this forever. Don't get excited. But I just wanted to give this out, especially because the last couple things we've done, there's been quite a bit. Doesn't feel like it, but if you look over this, we've actually done quite a bit. I think we actually stopped short last time about getting into the specifics about division.
Yeah, we kind of touched on it.
Yes. So let's do that. Then I'll let you guys try the back of this out, right? So don't look at the back yet. Oh, do I have mine? Yeah. So when I have a division problem, there's two major versions of a division problem. They're called sharing versus measurement. So let's break down what those might mean. And what's interesting is the math you do is the same, but the answer you get is interpreted differently based on which one it is. So here's what I mean. If I had 15 students and I want to divide them into 3 teams, how many students on each team? So is that obviously division? All right. This is a different kind of problem than if I have 15 students and I want to break them into, is that the same? Is that the one I want to do? Yeah, okay. Break into groups of 3. So the question here would be, how many on each team, right? And the question here would be, how many teams or groups? What's the math for each one? What math do I do to figure out each one? In fact, don't I get the exact same answer for each one? But do you see how the answer doesn't mean the same thing? And of course it doesn't mean the same thing. So here, I knew how many groups to share 15 students between. So this would be sharing. This one, I have to measure out 3 and then step back and see how many did I just create. So this one's called measurement. Does that make sense? Do y'all agree that the math I'm going to do in each of the situations is the same? I'm going to get the same damn answer, right? What answer am I going to get? Holy shit. So what's it mean here?
5 on each team.
5 people in each team. What's it mean here? 5 groups. 5 teams, right? You guys kind of with me? Now again, to us, we focus more on the math part of this, so we don't necessarily even see like a big difference, but you can see physically there is a difference, right? If I wanted to model the first situation using blocks, what would I do? If I wanted to model this first situation using blocks. Yeah, I mean, I'll plop down 15, right? You have to trust me, there's 15. There will be. There's 9, 10, 11, 12. I get to be like the little kids on there. Here, you're for 15. All right, let me see. 3, 6, 9, 12, 15. All right, and then I have the guy over here going, okay. All right, sorry.
Why did you get 15?
Because you said 2. All right, sorry. I just want some kid to go, because I think one kid went, because that's what it is. Now what would I start doing? I got 15 blocks down here, right? I could do it on the overhead. That would be unbelievably good teaching, but I'm not going to. Maybe I will. I don't know. The first question's a little bit freaky, right? I gotta make 3 teams. So how would I do that?
Make 3 piles.
Sure. Yeah, they'll be very specific. So I see what you're doing, but so I'll put 1 here, 1 over here, 1 over here. Okay, good, right? And then you go. Okay, so then to get the answer, I can just count how many's in each team. Are you guys with me?
Yeah.
Now again, that is a very specific physical situation. The math happens to be the same, but these physical situations are very different, right? How would I do the second one? Here's my 15, right? Use your imagination. Yeah.
I separate 3 and then another 3 and then another.
Yeah, and now I can kind of focus on, okay, I got 3, and then 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 I got 1, 2, 3, 4, 5. 5 teams. You guys see? Same answer, same math, very different physical interpretation. Are you guys kind of with me? And again, when you are a little human, math is something we made up on top of the physical world. So the physical world, we understand, I can touch that shit. So when I do this, this feels very different from the first thing I did. Are you guys kind of with me? And this is what parents, I forgot. Maybe I can get it. I ran across an image on some social media somewhere that's a perfect encapsulation of parents not understanding. And nothing wrong with parents, obviously. I don't blame them. So your students, the reason we have multiple ways to interpret, and we have to make sure students know how to interpret them, is because they relate to something physical that they can do. The next stage would be, okay, this is division, and then these two have the same answer, but they got different. So then we not separate, but we realize the math is its own thing. Are you guys at all with me? So I don't know, when I first wrote those 2 up, you probably very quickly saw the answer is going to be 5. Then you think, 5 means something different in each case, but it still wasn't that big of a deal. But when you actually do the physical work, you're like, this is a completely different way to do this, right? And I'm going to show you a video. Somebody's going to basically do what I just did. That's why I didn't care too much to show you. You'll see it. You see a little kid do it, and they're going to be cuter than me. Okay. So is that okay? Do you guys get the difference between sharing and measuring in terms of division? Basically, sharing, you know how many groups to break something up into. Measuring, you know how big each group needs to be. Okay. They're right here too. So, like we already said, and I thought for sure we did an example of repeated subtraction. We did a couple, didn't we?
Yeah.
I did one with the remainder too, if I remember correctly. All right, so for some reason I skipped this, because I don't think I did talk about sharing and measuring. So yeah, if I want to do 29 divided by 11, how would I use repeated subtraction? You would probably repeatedly subtract, but how would I do it and interpret the results? So I start with 29, and then I would
Minus 11.
subtract 11. Subtract 11, that's the repeated part, right?
Yeah.
So what's that 7 mean? I can't subtract 11 because currently negatives don't exist in our universe.
Your decimals exist?
Hell no, not yet.
Remainder.
We haven't done fractions, we haven't done decimals, we haven't done negatives. We've still done a lot of shit though.
Maybe.
So what's the answer? 2.
R.
Good, good. 2, big SR, 7. I like it. And we did talk a little bit about what remainders mean. If I take 7 away from this, it becomes a number 11 goes into. So 7 is the excess over a number that would be nice with 11. That's what remainders actually mean. Does that make any sense? It's a little weird for me because this morning I showed my pre-calculus students how to divide polynomials. And they always enjoy that. Right? Don't worry, I'm not going to do that to you. Even though part of me wanted to right there.
That would have been funny.
I don't know if everybody would say that. Yeah, good. We talked about missing factor. We talked about division by 0. What do you call it when I try to divide something by 0?
Undefined.
Undefined, good. And we talked about why it's called undefined. We talked about that last time. There is no number defined that when I multiply by 0, I'll get 11, because that's what would have to be true about the answer to this. Because when I divide something by something and I get a number, that means this times this is that. That's the number defined, that when I double it, I get 12. So the answer to this would have to be the number defined, that when I multiply by 0, I get 11. Nothing's defined that way. Undefined. Nothing magic. Yeah. Okay. Blah, 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 blah. Okay, good. All right, that catches me up to where I want to be. So let's do this. I want you guys to individually work on the other side of this. The group work's going to come later. Right now, I want you... So I'm going to kind of catch up to you guys a bit. This first one, I think all of us have lived this first one at some point. Yes? This is a very easy mistake to make. But looking into ways to address this issue. So what is it? Why would a student do this? 100 minus 27. Why would they think 83? Yeah, where's the 8 come from?
The 2 minus 10.
10 minus 2.
Yeah.
And then they just say 10 minus 7 because that's what the 0 represents, right? But not really, it doesn't represent 10, does it? So that's the issue, is this is just 0 and I can't take 7 away from it, right? You guys, but it's easy. We do this all the time. I see this all the damn time, right? A way to not do this. Does anyone think they came up with a way to...
You would make it 20, like you do 100 minus 20 and then you minus 7.
Okay, yeah, you gotta subtract 27. So if you subtract 20 and you subtract 7, you have subtracted 27. That'll work. So 100 minus 20 is 80. And if I take 7 away from that, 73. That's the right answer.
Can we say carry over correctly?
Oh,
Yeah, that's
one answer would be borrow,
Yeah.
put the 1 in. So that's the standard algorithm,
Yeah,
right?
Sure to jump.
This is more, how could they do it in their head? That's the question. Yeah, back here. Eric, did you have a suggestion?
Oh,
Same thing, okay. Anybody else do a different thing? Here's something cool. Subtraction tells me how far apart two numbers are, correct? Like, for example, how far apart are 10 and 8? 2. 2, because 10 minus 8 is 2. This is cool. You guys good? Isn't 11 minus 9 also 2? So as long as I add or subtract the same amount from each number in the subtraction problem, they will still be the same distance apart. And the whole point of a subtraction problem is how far apart are they? So what do I add to 27 to make it a whole number? 3. So then I add to 100 and add the same thing. So if I add 3 to both, well, that's easier. I don't need to borrow shit. 10 minus 3 is 7, 3 minus 0 is 3. You guys see that? You guys see that? Does anyone ever seen that? This is something called equal additions, which is not a very creative name, because what did we do? We added an equal amount to each thing, so equal additions. No? Yes? Maybe? No? Screw you? Okay. Yeah.
Can you have the kid just round up,
How do you mean round up?
like 27 rounded up to 30 to make it easier? And then, or is that?
Yeah, another way is sort of related to what you did, but if I do 100 minus 30, that's 70, but didn't I subtract 3 too much?
So then you have to add 3 now.
So
Let me see this again.
then you have to add.
So if I do 100 minus 30, that's 70, but I subtracted 3 too much, right? If I have $100 and I owe you 27, you took 30 away from me, that's not good. You with me? I'm like, what's that? Is that your supposed tip? No, you get that $3 back. So then I get, so I can do 100 minus 30, that's 70, and then add the 3 back on, that's 73. Again, I get the same right answer, right? You guys see what I'm saying? Now, for a parent who's done all this before and knows how to subtract, they're gonna say, all that shit's the same. Just teach them to carry the one with the shit. But there's more to it than just the rote method. I want a student to understand the idea behind it, right? We want them to be better than just, carry the one. Carry the one. No, I want them to know the idea behind these things, right? Okay. And of course, the whole carry the one thing, we're gonna actually see physically where that comes from. And I think I can't remember, I think we might have already seen that, I can't remember. Not carry the one, but borrow. What about number 2? I've already done one example for you, and I understand. This is weird as shit. What is that symbol, Jeff? Well, this symbol is weird. It's not weird to us because we've seen it a lot, but it's weird. What about this symbol? What the shit? If you really think about the division symbol, do you guys know what it's supposed to represent?
Fractions.
Yeah, it's supposed to represent like a fraction bar with a number up here and a number down there. Yeah, but still, it's kind of like, okay, that's nice, but that's just weird. It actually is weird. It's a very weird thing. To me, it looks like mine, right? Looks like 3 places. It's got a blueberry pancake and a blueberry. Anyway, no, let's not go there. Okay. So if I do, to check to see if this is commutative, I just want to know if 4 triangle 5, for example, does that equal 5 triangle 4? And I'm picking those because I've already done 4 triangle 5, or delta, let's call it delta. How do you do 5 delta 4? What happens? What does delta say I have to do to the first guy? I gotta double the first guy, and then I subtract the second guy. That's what that thing says. I always do that. That's what that operation says I do. And this really is not that weird. What's a square root symbol? Isn't that like a lot to it? It's not just, I gotta think backwards and I gotta tear it apart and so forth. There's a lot involved with that symbol, so there's symbols can have a lot involved. And of course, what's this? 6. 10 times 10 minus 4, right? Okay. Is that the same thing I got up here? No. So it is not. It's, what did we just check? We just proved that it is not. Are there any parentheses up here? Parentheses associate, individual numbers commute. What did each of us individuals do today? We commuted to school. Individuals commute, parentheses associate. I guess again, this is just a way to remember it. Okay, it's not some like prescribed thing. So when I turn the symbol, the numbers around, do I get the same answer? No, so it's not commutative. What am I going to need to figure out if it's associative? What's the least number of numbers I need to check to see if it's associative? 3. So I want to check. For example, since I already got 4 or 5, let me do 4, 5, 2. Is this the same thing as 4 delta 5 delta 2? That is how to check to see if something is associative. Let me stop for a minute. From one side to the other of that equation, that equals, what moved? The parentheses. So when parentheses move, that's associative. When individuals move, that's commutative. Did any individual number move from where they were in relation to the others? No. Nope, it's 4, 5, 2, 4, 5, 2. So that's not commutative. The parentheses got up, that's associative. Is that cool? Or is that understood? Maybe not to the level of cool and understood. Okay. So this one's nice because I already know what this is, right? What is this? We already figured it out. 3. What's 3 delta 2? How do I figure that out? Yeah, so the way it works is it's twice the first number minus the second number, so I get 4. So this side works out to 4. Let's figure out this side. How do I figure out 5 delta 2? What's the delta function always do? The first number I double it, and then I subtract the second number. So what's 5 delta 2? It'll be double 5 minus 2. 8. And then how do I do 4 delta 8? 2 times 4 is minus 8? 0. Are these the same? No. So when I move the parentheses, does the answer remain the same? No. So this is not commutative and it's not associative. Okay, I like it. I understand that you didn't like that problem. I understand. One reason we look at problems like this is because, isn't this weird? Why is this weird? Why is this weird? Never seen it before. The people you're going to be teaching, could they be people who have never seen a division symbol before, for example, right? So this is, again, one reason we do some of this is to put you on the level of a student and go, this is how they're going to feel. Keep that in mind when you're doing what you're talking to them about, so you don't become like that one video I showed some of you guys the other day. Smooth the thing closer. So if you missed that, I can send you a link if you want to. Is everybody with me so far? So that's one reason we look at this. And another reason is because to really understand commutative and associative, we should look at things that aren't either. So subtraction isn't, but we know subtraction. So let's look at something weirder. How do you really check to see if it is? You gotta really get into the nitty-gritty. Okay, maybe. And there are some homework problems that involve these kind of weird things, like number 3. I don't know if anybody had a chance to do number 3 yet, or even understand number 3.
It's weird. I understand it now.
So when we made a multiplication table, 0, 1, 2, 3, 0, isn't 0, 1, 2, 3, aren't they just symbols? Haven't we given them meaning? So when I say 1 plus 2 equals 3, we can memorize that, we can talk about why that's true. But on one level, it's just symbols. The 1 symbol, when I do the addition symbol with a 2, I get a symbol of 3. So this omega, and I remember in grad school, the teacher would talk about something and we would have no idea, so we say it was the omega syndrome, because the concept would fly in, go overhead, and fly away. So it makes this symbol, omega. That was just for us, I guess. Do you see how this is read? It's exactly like a addition multiplication table. So I can think of this as plus if you want to. A plus B is B. Do you see? So if I call it plus, maybe sometimes it's easier to think about. Are you guys all with me? So 1 is a symbol we've chosen to mean one thing, for example. These are just symbols. This is some operation. It could be times, it could be plus, it could be delta, it could be some other thing that they didn't tell me about. Why do I not care? Because I have all the answers. Can you tell me what C omega D is? D. What is D omega C?
A.
So does this represent a commutative operation? When you do D omega C, do you get the same thing as when you do C omega D? Did we get the same thing just now?
No.
No, we didn't. When we did this, what did we get? C. And when we did this, what did we get? C omega D was D. There we go. And C omega D was A. I like it. No, you'll get it right, Jeff. D omega C is A, and C omega D is D. Is that true?
Yes.
Is A equal D? No. Okay. So is this commutative? No. Okay. Are there some situations where it is true? I don't.
Anything with A is B.
Yeah, so what do you think? If this was a times, what do you think A is related to? 0. Do you see that? Or not really, I guess it's not really that. B might be, see this isn't, you can't really make it into one of ours. I tried to make it as freaky as I could, and I did. You can't really relate it to it.
You really did.
I did, I'm good at
If
that.
if AA was C, it'd make more sense.
True, yeah, you can kind of, if the point of this class was to look at a bunch of these, which it isn't, you can start to make, realize that the diagonals are important. Yeah, so you notice that the top one is not C, it would make more sense, yeah, okay. Enough of that. Okay. Again, we're just looking at the idea of operating on two symbols. So when we use numbers, those are symbols that have physical meaning, and when he's in operation, they're one of the basic operations, plus, minus, and we understand what those mean. This is just a higher level of that, these are just symbols, and again, the people you're gonna be talking to, very often, the little humans, are not gonna have worked with these symbols much, the symbols we have. Alright, who's got number 4 figured out? Anybody? Yeah. Okay, let me ask you this, let me ask you a question kind of related to this. Can somebody tell me what's the smallest set of numbers that is closed with respect to multiplication? 0, yeah. Because anytime you take an element of the set, you multiply it by another element of the set, you still stay in the set. 0 times 0 is 0. It also happens to be the smallest set closed with addition, right? 0 plus 0 is 0. You with me? Now, but that's not what this says. I just want to kind of get us thinking in this direction. There's a set that is closed with respect to multiplication. Does that mean it has to be closed with respect to addition? No.
Wow.
Alright. Does anyone have any idea about how to start investigating this? So what is it? Go ahead.
Well, multiplying is adding.
Yeah.
Multiplying is
Dividing
repeated addition, sure.
Yeah,
Yes.
and dividing is.
But be careful, that doesn't mean, let me give a little example. What's 1 times 1?
1.
What's 1 plus 1? Okay, can you come up with a set that is closed under multiplication that has a 1 in it? What was the smallest set closed under multiplication?
0 plus 1.
Now, if you add 1 to it, is that still closed? Under multiplication. If you take any element of the set 0, 1, and you multiply it with another element, do you get something not in this set? 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. If you add 2 elements of the set, and again, 2 elements means it could be the repeat, is there ever a situation where you have to go outside of the set to get the answer?
Yeah.
Yes, 1 plus 1, right? So one way to answer, this is true. Sometimes your students will have a question, and the quickest way to answer it is with a counter example. Because they'll do something like, when I divide, it seems like I always get an even number. 8 divided by 2 is 4, 16 divided by 8 is 2. I always seem to get an even number when I divide. Well, how do you show them that's not true?
We divided by 3.
Yeah, you take like 9 divided by 3 or something, you know. So there you go, you just happen to be picking ones that happen to come out even. Does that make sense? Sometimes the quickest way to answer a student's question is with a counter example. Here's a situation that doesn't match what you thought would happen. Do you guys follow? No. You don't want the answer. Okay. Alright. So I just wanted to get you ready with this because there are a couple problems in the homework that deal with these kind of weirdly defined operations. And again, it's because we are all very familiar with the 4 basic operations. So to really get on the level of the idea behind them, we must use an operation we're not used to really make us stop and think. Right? Okay. Alright, I like it. And you guys are like, well, that definitely is what this is. Okay. What would, the minute I do this, how do I add, how many numbers do I have to add so that it's closed with respect to addition? I think there's a question in the homework exactly like this. The minute I put a 1 here, how do I make it closed? Can I just put a 2 and then it's closed? No, why?
Just get like
1 plus 2 is 3 and 2 plus 2 is 4. So what if I add 3 and 4? Is it closed then? No. So how many numbers would I have to add to make it closed? Infinite. I have to add all the whole numbers, right? You guys semi with me? I'm pretty sure there's a homework problem just like that. And you're like, okay, maybe I'll get to it, Jeff. Okay. All right. You guys with me though? So the idea of closed, somebody was asking me about it earlier because I know, I love the name because it says, if you take two things in the home, can you stay in the home to get the answer or do you have to go outside? If you have to go outside, it's open. If you can stay in the home, it's closed. You don't have to open the door to go get the answer. So if I have 0, 1, do I have to go outside the home to get the answer for addition? Yes, 1 plus 1 is 2. I have to go outside of the set to find 2. That's not closed. Okay. Okay. I'll stop with that. So I want to do a little bit out of section 3.3, and then I have a sheet that's going to be group work from the beginning, and it's going to involve at some point coming up and grabbing stuff and showing me things. Right? Actually, maybe I'll show you some videos real quick. I'll show you some cute little kids, and maybe you won't be as upset about Omega. Okay, let me see. Ah, shit. Here's what I gotta remember my password. Holy shit. Okay. It's a miracle. Alright, so I'm gonna show you a few videos. I gotta stop this dude.